of material to cover. We have to continue, and we cannot stop now. We have around 4 more chapters to be covered, including this chapter. This is theory, and we have 3 applications. Three chapters on application. Okay. So what is this chapter on? This is on fatigue failure theory. So what is fatigue failure theory? This is about dynamic stresses and failure due to dynamic stresses in the components. So let's start with a new slide here. 1. Okay. So what is fatigue? Fatigue failure theory. So this deals with dynamic stresses, not just dynamic loads, dynamic stresses to be more accurate. When the component has dynamic stresses or varying stresses, stress is a function of time, then it leads to a phenomena called fatigue theory. The best example of a fatigue phenomena is if you take a piece of wire, a thin piece of metallic wire, and you want to break it. How do you break it? Can one of you tell me? How can you break a piece of wire?
You just move it up and down.
Okay, so you
Both.
bend it up and then
Yes.
bend it down, correct? And you repeatedly do this. When you repeatedly do this, then the wire cracks. The same wire, piece of wire, you try to break it by applying a tensile load. You cannot break it with your hand. Rather, you need a machine, or you need to tie up the wire, and in the other side of the wire, you need to keep adding weights. And it will take huge amount of load before the wire actually breaks. So under normal static loads, tensile loads, the wire takes a huge amount of load. It has a capacity in comparison to the bending moment load. It has a huge capacity to carry the load. The same piece of wire, if you take and if you apply a dynamic tensile and compressive loads, okay, you will still find, although lesser than the usual strength of the material, here the strength of the material will be Sy, while here it will be observed that slightly less, not slightly, a lot lesser here. Okay, so here we will deal with fatigue phenomena. When you apply tensile and compressive loads, or just tensile load, maybe you will not be able to apply compressive load on a thin piece of wire. So what we can think about is the value of P ranges from 0 to let's say around maybe 20 kgs or 30 kgs we apply. Okay, 30 kg load, so 30 G will be the newtons. And if you keep on increasing and decreasing in cycles, you will find again this undergoes fatigue failure. Okay, now this will have significantly higher capacity still. So we are going to see what is called as endurance limit under tension. But when you apply the bending moment load, it is even lesser. Under bending moment load, it will be SE value, which we call as endurance limit. You are going to see it is going to be, stress value is going to be much lesser, and it will break even faster. So the rule in design is always avoid bending moment load. This is the worst type of load you can apply. Bending moment load is the worst type of load. And if it is cyclic, it will break very fast. Okay. All right. So let's go to the fatigue phenomena here. And what are we going to learn regarding fatigue in this class? So the first, we are going to see different theories. The first theory is called as the stress life method. In this method or theory, we are going to calculate stress and then predict what will be the life of the specimen, how many cycles of load the particular specimen can take before it undergoes fracture. We are going to predict life. So in fatigue phenomena, one of the main objective is life. Life is the important parameter that is to be predicted. So stress life method, there is also another method called strain life method. We are going to see this as well. So using the strain, we are going to predict what will be the life of the specimen. And finally, we will have linear elastic fracture mechanics, which is the same type of equation we have seen in chapter 4. Okay. So these are the three methods, and we are going to go through it. First, we will see experimental, what kind of experiments have to be done in each method. For example, in stress life method, in strain life method, we are going to see what kind of experiments are done, and then we will go through equations. Okay. All right. So let's go to the slides now. So this is the concept map for the entire chapter. Stress life method, first experiment, and then strain life method. First we will go through again experiments, what kind of experiments and what kind of data are extracted, and finally for both the methods we will go through the equations. So let's go to the slide. Okay. Okay. So there are some other information also here. As we go through the slides, we will come across that information as well. Okay. So loading produces stresses that are variable repeated. It could be repeated loads, it could be random repetition, could be alternating or fluctuating. Okay, both are possible. What is alternating? Positive and negative values. Fluctuating could be either in the positive zone or in the negative zone, or maybe unsymmetrically in the positive and negative zone. For example, I can vary the stresses in various ways. You can have nice positive and negative values, or you can have random fluctuations like this. Okay. So this is stress versus time, stress versus time. So that is what is being said here. Maximum stresses, when you apply in the fatigue phenomena, especially in the stress life method, you are going to see they are well below yield strength. In the strain life method, may be close to the yield strength. So even though we apply stresses well below the yield strength on the material, still the material will fail even though it is below the yield strength. And that is why this is a very dangerous phenomena, and fatigue could cause a failure or a fracture on it. Failure occurs after a certain number of cycles. Failure is by sudden ultimate fracture. That means the fracture takes place due to brittle fracture phenomena, maybe at the later stage. But the initial stages, when crack propagation takes place, we are going to see that maybe it is not brittle phenomena as such. Okay. No visible warning in advance of failure. We usually, when crack propagation takes place in fatigue phenomena, just like you bend the piece of wire, you never have any warning that the crack has formed. Suddenly it breaks. Okay, no visible warning. That is fatigue phenomena. Now this is a airplane Due to fatigue phenomena, the fuselage, maybe the underbelly or maybe even the top of the aircraft structure, due to fatigue phenomena, it completely broke off while flying. Okay, so this is one of the dangerous events that happened due to fatigue phenomena. So let's see if I can run a video for you guys. Let's see. It is important to watch this video. You will understand better what are the practical implications of fatigue phenomena. So let's go here, fatigue loading. This is one. Okay, so this is the okay. So there are two videos. I will run the experiment later, but this is a practical situation where you had a problem. Please let me know if you can hear the audio. Can you guys hear the audio?
Yes, Doctor.
Yes, Doctor.
Okay.
Maui Tower, Aloha 243.
Aircraft calling tower, say again.
Aloha 243 for inbound landing.
At 1:48, 3 minutes after the explosion, the crew makes their first voice contact with the ground.
We are unpressurized. Declaring an emergency.
Aloha 243, say your position.
We're just to the east of Makina Point. Descending out of 11,000. Request clearance into Maui for landing. Request the emergency equipment.
The crew fears that critical wiring and control cables may have been severed.
Let's try flying with the gear down.
All right, you got it.
There are lights to indicate whether or not the landing gear has safely deployed. The main undercarriage has extended as normal. But the light showing that the nose wheel has extended doesn't come on. Though the forward undercarriage has extended, the crew still can't be certain whether it's locked in place or whether it'll collapse on landing. If it doesn't hold firm, the aircraft, traveling at close to 200 miles an hour, will smash nose down onto the tarmac.
One reverse.
Okay.
Thrust reverser.
Aloha 243, just shut it down where you are.
Okay.
Everything's fine. The gear did it.
Okay. Shut it down.
In this extraordinary video captured moments after landing, the amount of damage the airplane suffered is difficult to comprehend. An emergency evacuation of passengers who escaped injury has just been completed. Some injured passengers have still to be helped from the plane. How it flew for those 13 terrifying minutes seems astonishing.
Okay, so this is in the last part of the video, you saw the actual aircraft. You can see the damage that is caused on the aircraft due to your fatigue phenomena. What has happened in forming the aircraft body here? They use rivets, and these rivet pins, they have undergone enough number of cycles of load, and because of fatigue, the rivets gave up, and the entire composite structure, whatever they have used, aluminum and composite structure, just blew off after the rivets gave way to the forces acting on it. Okay, so this is what happens when fatigue phenomena happens. There are also other similar dangerous events that can take place, especially if you have a rotating shaft with very high speeds. If it undergoes fatigue failure, again the shaft will break, the pieces will fly around and act as very high velocity projectiles, killing people around. Okay, so again, fatigue phenomena is very dangerous. You have no warning, and it can lead to loss of life and huge property loss. So this particular Aloha flight worth several millions of dollars. Again, you can see what happened to the flight. Okay. So what happens in fatigue failure? There are approximately we can say there are three stages in which the fatigue failure proceeds. Fatigue failure usually starts with stage 1, where you have initiation of cracks. The cracks are initiated in A. For example, this is a shaft with some threads here. I think this is a bolt. It's a piece of bolt. And right on the surface of the bolt where you have threads, you have change in geometries. For example, if you look at the thread, this is the V threads. If you have a geometry like this. These areas, they act as places where there can be enough stress concentration, and because of these stress concentrations on the V threads, what you will have is crack initiation. Very high stresses right on the surface, you can have crack initiation. And how these cracks are formed initially, if you look at it, these cracks are formed because of local plastic deformation. First, plastic deformation happens. Lot of slips happen. Okay, if you remember what is slip phenomena, again, slip phenomena is where you have dislocation motion, and if a lot of dislocation motions happen, then you will have a slip plane form. And a lot of slip planes, if they come on top of each other, they form into what is called as microcracks. So we are just seeing what happens at micro scale first. So microcracks are formed on the surface, and when you apply cyclic load, these microcracks, they close and open. For example, the microcrack, if you exaggerate, looks like this. And when you apply cyclic load, the cracks close and open, and because of that, the cracks become bigger and bigger in size on the surface. So this is the stage 1 of the crack. Stage 2, again, the crack grows from micrometer length to larger lengths, and they go into the depth of the cross section. So this is the cross section you see for the bolt. They propagate, the crack propagates, and then they go into a certain depth. So this is the region A, what you see here. This is the initiation region. Then as the crack grows and goes inside in depth, okay, maybe it's very small crack, it goes inside in depth, what happens is it starts forming what is called as beach marks. What are these beach marks? If you go to the sea and look at the sand, because of the waves, you will have beach on the sand, you will have many marks like this. In the same way, due to the cyclic load, many beach marks are formed on the cross section. So this is one of the signs. For example, if you don't know why a particular component fractured, you can look at the fracture surface, and if you see these beach marks on the fracture surface, these beach marks could be in any shape. It could be come in circular shape, etc. So there will be several waves. If you see that, you can be sure it is a fatigue phenomena that led to the fracture. Okay, so this is the stage 2. Now, when it reaches the end of the stage 2, what happens here? There is only a small portion of the material that is in contact for the entire material. That means only this area will carry the entire load. At this point, what happens is, since we have a very small cross section carrying the entire load, this entire area has become strain hardened and it has become brittle. So at this stage, stage 3, the material at the joint here has become brittle because of strain hardening phenomenon. At this stage, there is catastrophic fracture and immediately the material will fracture because it cannot carry the entire load. Okay, so this is the stage 3 of the crack. Okay, so now we can understand why at a very small load, much lesser than the yield stress, the fracture takes place. Why does the fracture take place? Because there is already micro cracks which are formed. These micro cracks, they propagate inside and then cause fracture during the fatigue phenomenon. Also, in last chapter, we solved an example problem. If you recall, in the example problem, what did we see? We saw that whenever there is a crack present in linear elastic fracture mechanics, whenever there is a crack present in the material, then the material fractures at a stress value much below the yield stress value. Okay, let's try to recall here. Again, if I go to one of the example problems here, I think this is the example problem. We considered a plate. Yes, we considered a plate with a crack present in it, and we found that the material cracks at 88.4 megapascals, but the yield strength of the material is 240 megapascal here. Okay, but the presence of crack is much less than the yield strength value, which is equal to 240 megapascal. But the critical stress under which the crack propagation happens and the plate cracks is only 88.4. So the presence of the crack reduces the load carrying capacity of the material, even in static loads. But in dynamic loads, it is going to be even lesser than this value. Okay, because of the dynamic loads. So the presence of crack explains the fatigue phenomenon. Presence of crack reduces the load carrying capacity of the material, especially in dynamic loads. So here are some examples. For example, if you apply a high nominal stress versus a low nominal stress, what are these stresses we are talking about? Which one is high, which one is low? How will we know which is the high stress and low stress in comparison to the yield strength of the material? Okay, so when it is close to yield strength of the material, we call it high nominal stress, and when it is much less than the yield strength of the material, then we call it as low nominal stress. Okay, so we should say much less than the yield strength. Okay, so there are three conditions here. We can see a plain shaft, a shaft with a shoulder with a smooth fillet, a shaft with a shoulder but having a sharp corners. Okay, so obviously this case will lead to very high stress concentration. There is stress concentration here and there is no stress concentration here. So first let's compare the results of how the cross-section fracture surface looks like in the case of low nominal stress without any stress concentrators here and here. Okay, so in the case of low nominal stress, we can see this is the A, A region where we have stage 1 initiation. We have a huge region where we have stage 2, okay, B region. And then we have a small region where the material cannot take the load and then fractures. If you compare with high nominal stress, we can see the region which carries the second region where we have the crack propagation is much smaller, and the brittle fracture takes place in this huge region. Okay, so but just by looking at the cross section, we can also figure out whether there are stress concentration effects, and secondly whether we have failure due to high nominal stress or low nominal stress. So how do we figure out? In the case of low nominal stress, the cross section is able to carry the load even though only a small portion of the material was stuck together. Okay, it was able to carry the load because the stress is low here. So the sign is, you will see that the final region where there are no beach marks and where you have brittle fracture, if it is small, then most probably it is low nominal stress in comparison to yield strength. And if you have a huge region which has brittle fracture, then you should know that it is a high nominal stress. Now, how do we know there is no stress concentration effect? You can see all the beach marks are smooth and concave from the top. However, if you have stress concentration effects, you can see the beach marks are disturbed. Okay, you can see the curve going up and down like this, and in that case you can come to a conclusion there is also a stress concentration effect on it. Okay. Okay, so here what kind of load have we applied? That is also important. We can see here tension and tension compression loads, mainly due to tension and tension compression loads. With the stress concentration effects, with the sharp corner here, you can see slightly different behavior on the cross section. So not every cross section looks the same. If you have a rectangular cross section, again you have different effects because of the corners. You will have stress concentration effect automatically. Okay. Now, how does a bending load failure look like? Again, in the case of bending, you can see different kinds of effect in comparison to the mere tensile and compressive load. Bending load, you will usually see the failure takes place at a much lower load in comparison to the yield strength. And again, we will have compression. This is, in this case, we have unidirectional bending. Since we have unidirectional bending, still we should have compression and tension effects on the top and bottom. Yeah. So this is for completely reverse bending. Again, you can see beach marks on two sides. It indicates we have reverse bending. How about torsion? In the case of torsion, again, mostly we will have the material in the center stuck for most of the cases, and then fracture happens in the from the center. Okay, so most probably if it is at the center, maybe torsional loads, but we cannot be sure just by looking at the cases. Okay, so even in the let's say this is completely reverse bending, even here we have some kind of fracture where in the center we have the material stuck together for the last stage of fracture, and we cannot be very sure about what kind of load was applied just by looking at the surface. Okay, so in torsional failure, you will most probably you will have a 45-degree shear failure if it is a let's say here. Okay, in torsional case, you should have a vertical failure if you have a torsional load which is applied. Most probably not a 45-degree failure, but in this case, it looks like we had a 45-degree failure, fracture surface. And let's check in the previous cases, when you apply the tensile load, probably you will have a 45-degree angle failure. Okay. All right. Another example here, you can, just by looking at the cross section, this is a real picture of the fracture surface. Can one of you tell me where is the crack initiation point? Can one of you tell me? Are you guys listening?
Yes, doctor. I think at B.
At B. Okay. So here this is a keyway to a shaft. Okay. Clearly this is a keyway to the shaft. If you don't know what is a keyway is a place where we put a block of material to connect the shaft to a gear or some other part. So let's see, shaft, keyways, and so you can see in this picture clearly. So this is the shaft and this is the keyway. And we connect the shaft to a hub through these keyway and keys by inserting the key in this gap here and then connecting the hub to the shaft so that it can transmit the torque. So most of your shafts will have the keyways. But the presence of the keyway leads to stress concentration effect, and you can see crack being propagated here. So this is the crack initiation area. Now this area, so this entire area you can consider it as a crack initiation area. You can see the beach marks here. So all these convex marks, all these are beach marks. And finally, this part of the shaft was in contact before brittle fracture. This is the final stage. Here the brittle fracture happened. Okay, so clearly a shaft is used for torsional loads, and because of torsion this has failed, and you can see the brittle fracture area is within the cross-sectional area and confirms that it is a torsional load that led to the failure. Now, is it a high nominal stress or low nominal stress? Here we can see the area which was in contact, which underwent brittle fracture in the last stage is very, very small. So since this is very small, it means low nominal stress fatigue failure has happened. And most probably the shaft has undergone huge number of cycles before failure. So just looking at the fracture surface, we will be able to figure it out. How about this? So we have here certain grease holes. Again, you can see crack initiation because of the hole here, and there is a huge area with beach marks, low nominal stress, and you can finally see here a small area which has undergone brittle fracture here. Again, low nominal stress, and most probably torsional loads, or maybe combination of torsional and bending loads. This is another example. Again, wherever we have hole, that is the place where we have initiation of cracks, and then we can see the beach marks here in this region. All this region, this is all beach marks, and then this entire region is brittle fracture. You can see very shiny, rugged surface, and the surface shows that brittle fracture has happened. Okay, and since this area is extremely large, that means high nominal stress. Okay, so this is a forged connecting rod. So a connecting rod cross section. This is the cross section of the connecting rod. Very high loads have led to the failure here. Okay. Now it says crack initiated at flash line of the forging at the left edge of the picture. Okay, so there is some kind of a manufacturing defect in the material. The manufacturing defect, maybe these are the crack points. You can see crack propagation here, and that led to the crack propagation and then finally failure of the material, ultimate fracture of the material. So this entire region is fracture of the material due to exceeding loads. And you can see here, this is an I cross section or a H cross section. Let's see here. Okay, so this is a piston rod of alloy steel here, used in a steam hammer. And what happened? Loaded axially, it was loaded axially. Crack initiated at the forging flake internal to the part. So there is some kind of a defect, manufacturing defect again, right at this point. This is the initiation of the crack right in the center. Then you have beach marks all around, and then finally this rugged surface shows we have brittle fracture again, huge area. So we can say the nominal stress is not very low, not very high, somewhat in between. That has led to the fracture here, fracture phenomena here. Again, more examples. If you have any embossing, embossing is when you write any letters or any signs, company signs on your component. Even these points act as stress concentration areas, and they can lead to crack in the material. So this is case of a flywheel, I guess, cake oven car wheel, I don't know, whatever it is. So again you have failure. Again, this is a lubricating hole, fracture proceeding outside. This is the beach marks you have, and finally brittle fracture in this area. So this is an aluminum landing gear, torque arm assembly, used in aircrafts for landing gears, and this has also undergone failure. Okay, so that gives you some idea about how a fatigue fracture surface looks like. So we are going to go through three models: stress life method, strain life method, and linear elastic fracture mechanics. So what is stress life method used for? When we have low nominal stress in comparison to the yield strength of the material, then we use stress life method. So we just talked about low nominal stress. In this case, we use this method. If it is high nominal stress, then we use strain life method. And in case we know there are cracks present inside the material, then linear elastic fracture mechanics. Again, we can use that the ideas of stress intensity factor and critical stress intensity factor or fracture toughness here also, and predict what would be the life of the specimen. Now again, in fatigue life method, it is called life method because we are predicting what is the life of the component, and it is very important for your design. Okay. So let's learn something a little bit more about stress life method. It is least accurate method. That means this is the easiest method as well. And we are going to use stress life method initially for any design of the component. Before you go and do finite element analysis, you need to do manual calculations by hand. And this is the method we are going to use and do that. Okay, so it is also called low cycle. This is not low cycle, sorry, it should be low nominal stress. but should be a high cycle method. So this is wrong. It should be high cycle application. Why do we call it as high cycle applications? Because the failure takes place after undergoing, let's say, nearly 1,000,000 cycles. Because of low stress, the life will be more, and close to 1,000,000 cycles or less, slightly less, but definitely higher than 1,000 cycles. So anything higher than 1,000 cycles is called as high cycles, and for that we use stress life method. Most traditional, easy to implement. Strain life method. What is strain life method? We will see in detail later, but for now take it for granted that it is near the yield strength. Sometimes it can also be slightly above yield strength, leading to plastic deformation, localized plastic deformation in the component. You don't have plastic deformation in the entire component or entire cross section of the component. Rather, we may have at localized points. So in those cases, we use the strain life method because it is more accurate, and still we will have several assumptions to strain life method, just like stress life method, and therefore we cannot be too sure of it. Nowadays, in strain life method, we will combine experimental results with finite element analysis, and we will be able to get much more accurate results using strain life method. Okay, finally we already saw what is linear elastic fracture mechanics. Okay, so first we will go to experimental part of the stress life method. So what is an experiment? Just like a tensile test, static tensile test, we will be able to do also a fatigue test on a specimen. According to the standards, the standard size of the specimen and the shape of the specimen should be like this. To conduct any experiment for stress life method, the first person who conducted an experiment for stress life method is a German engineer by the name Wöhler. Okay, Wöhler. And that is the name of the guy, and the experimental results are also named as Wöhler curves, the results which we get out of the experiment. We will see what is the experiment. In the experiment, we take the test specimen and we subjected the test specimen to repeated cycles of stress. What kind of stress? It could be bending stress. It could be tensile and compressive stresses. It could be torsional stresses in cycles. Okay, mostly we do bending and tensile and compressive stresses. If you do the bending, if you apply bending stresses in cycles, then it is called as R.R. Moore high-speed rotating beam experiment, where we apply completely reversed bending stresses on the specimen until it breaks, until it fractures. In this stress life method, we apply the stress in a controlled way. So how do we apply the stress? Stress life method, experiments. So let's say this is the y-axis is the stress, and we want to apply a bending stress. We will apply in a cyclic way, just like sinusoidal curve. So there is a maximum value, sigma max, and the minimum value of stress, and there is a frequency of the stress as well, cycles. So the max value, if it is equal to the minimum value of the stress we are applying on the specimen, then it is called as completely reversed loading. And this is the way we apply the stresses on the specimen. Completely reverse loading. Okay. It is possible that sigma max and sigma min can be different, but to simplify our situation, we always apply in such a way that max is equal to minimum. Now, this height of the stress, we can call it as sigma amplitude, and the mean value of the stress also we can get. So first, let's define amplitude of stress. The amplitude of stress is defined as sigma max minus sigma minimum over 2. We will need these definitions to make some plots for the experiment. Sigma mean, so this will become equal to sigma max value because max and min are equal. Okay, and remember we are talking about the magnitudes are equal. Sigma min value will be a negative value, so minus of minus will become plus, and that will become equal to sigma max. Sigma mean value, on the other hand, since the magnitudes are equal but opposite in sign, will become 0 in completely reversed loading. Okay, so with this condition, we can do some experiments for the stress life method. Now, let's see here. Specimen is carefully machined and polished. So any test specimen we take, it is very important that we have a mirror finish to the surface of the specimen. So it is highly controlled experiment, and we do not want to have any surface defect, no cracks, no roughness on the surface. All these things will reduce the life of the specimen, and we want to check for an ideal specimen with no defects on the surface. So we must have a polished, mirror finished surface and well machined surface. And for this kind of standard specimen, we do the experiments. Okay, so first I'm going to run another video to show you how the experiments are conducted, and then we can go to the graph here. Are you able to hear?
Fatigue test.
Are you
Many everyday
Are you guys
Yes,
able to
sir.
hear the? Yes. Okay.
items are not loaded uniformly, but rather non-uniformly with periodically changing loads. This is quite obvious.
Let me play from the beginning.
Fatigue test. Many everyday items are not loaded uniformly, but rather non-uniformly with periodically changing loads. This is quite obvious in off-road biking. Frames, handlebars and wheels are subjected to high alternating mechanical loads. It is just as obvious in the case of a garage door spring. The spring is unloaded when opening the door and loaded when closing the door. The connection rods of this old compressor have endured a large number of rapidly changing tensile and compressive forces. Even when cycling quite moderately in the city, many components are exposed to periodically varying loads without us being aware of it. The crank arms are alternately under load, then swing back almost load-free, are under load again with the rhythm of pedaling. The spokes, the pedals, even the individual links in the chain are stressed periodically. Also, the railway bridge over the River Rhine, seemingly totally addressed, alternately has to bear the additional burden of a heavy freight train and then only its own mass. Aircraft experience quite different stresses during takeoff and in turbulence than on ground. This type of loading is generally termed fatigue loading, and the material responds to it, fatigue. The term fatigue is used because it takes some time for the failure to occur under repeated loads. The problem with materials is that they normally endure less at repeated loading than with a once-only load. The wire does not break when first bent, but bending it back and forth repeatedly leads to an early fracture. This bicycle crank arm had only been able to endure the cyclic loading for a certain time before it broke. The fate of the garage door spring was the same. It had borne the opening and closing of the garage door about 60,000 times before it finally fractured. The broken exercise equipment, a torn blade of a fan, a bandsaw blade full of cracks, the broken screw, a defective universal joint, and many other examples show how important this phenomenon is. Each day, thousands of items break due to cyclic, often repeated loading. How can we make sure that all these components withstand the cyclic loads? To achieve this, one has to test the materials appropriately. We intend to measure the fatigue strength of a frequently used steel in our laboratory. Hot-rolled steel rods made from the structural steel S235JR are used as base material. In order to eliminate the influence of the surface and to stress the material in a well-defined manner, suitable specimens have to be machined from the rods. This specimen type would be ideal. The shoulder-shaped ends have been designed for safe gripping. The actually tested region is cylindrical with a diameter of 6 millimeters. The material tester goes to the workshop to get 10 specimens manufactured from the rods, not just one. All of the specimens are as identical as possible. Back in the lab, he has all specimens ready for use and picks out the first one. He mounts the specimen carefully and securely into the fatigue testing machine. Together with 2 half shells, he inserts one end of the specimen into the right specimen grip. With a union nut, he locks the right end of the specimen. Likewise, he mounts the left end of the specimen into the left specimen grip and tightens the nuts. The preparation is now complete. The material tester then selects the appropriate test parameters on the control computer. He intends to load the first specimen alternately with a tensile force of 7 kilonewtons and a compressive force of 7 kilonewtons. The mean force is 0. A click on the start button and the testing machine begins to stress the specimen periodically. Our fatigue testing machine is equipped with a mechanical resonance drive. The specimen is connected at its left grip via a load cell to the machine frame. At the right grip, a spring is mounted, and there in turn a mass. An imbalance stimulates the mass to vibrate. Longitudinal guides prevent the mass from vibrating in the transverse direction. Via the spring, the test force acts on the specimen. By varying the excitation frequency of the imbalance, the test force can be controlled. In our case, the specimen is loaded with about 25 cycles per second. Meanwhile, the first specimen has already endured over 300,000 load cycles and still seems to be intact. In reality, however, several cracks have already developed starting from the surface, the so-called fatigue cracks. With each load cycle, they grow a bit further into the specimen. The biggest crack gains the upper hand, grows the fastest, and finally leads to fracture after 381,000 load cycles. The first test is finished. The material tester removes the fragments cautiously and inspects the fracture surfaces. At first glance, the fracture surface looks unimpressive. A closer look reveals 2 regions: the rather dull, predominantly flat fatigue crack propagation area and the rough residual fracture area. The residual fracture area results from the final catastrophic rupture. The fatigue crack propagation area has developed during the cyclic growth of the fatigue cracks starting at the surface of the specimen. What does the fatigue crack propagation area look like at higher magnification? One of the fragments is carefully placed on the specimen stage of our scanning electron microscope. Now we can investigate the fatigue crack propagation area in detail. In some places, but not everywhere, parallel grooves and ridges can be seen, the so-called fatigue striations. Each groove and each ridge has been formed by an individual load cycle, a typical phenomenon. Of course, now we want to know how many loads.
This is the beach mark here. He's talking about beach mark as fatigue striations.
Cycles this material can endure with other loads. For this purpose, the material tester picks the next specimen from his supply and installs it into the fatigue testing machine. He chooses a higher alternating load for the second specimen, a tensile force of 7.5 kilonewtons and a compressive force of 7.5 kilonewtons. Under the increased load, the specimen is only able to withstand 43,600 cycles to failure. The third specimen is only tested with a cyclic load of 6.5 kilonewtons. Under this reduced load, it does not break even after 3 million load cycles. Additional specimens complete the series of measurements. Some of the specimens are tested with the same load we've already used. In this way, we get an impression of the range of scattering. To compare materials in a fair way, the different cyclic loads are converted to the respective stresses acting in the specimen. In this case, the stress alternates sinusoidally around the mean value, which is termed mean stress sigma m. In this series of tests, the mean stress is 0. The stress amplitude is labeled with the symbol sigma a. For graphical representation, the SN diagram is used, also termed Wöhler diagram. In an unusual manner, the predetermined variable is plotted upwards on the y-axis. It is the stress amplitude sigma a. And the result of the test, the number of cycles to failure n, is plotted to the right on the x-axis. To fit small and large numbers into the diagram, the x-axis is not scaled linearly, but logarithmically. The first specimen was loaded with 7 kilonewtons. This corresponds to a stress amplitude of 248 newtons per square millimeter. Under this stress amplitude, it broke after 381,000 load cycles. The second specimen was loaded with 7.5 kilonewtons. This corresponds to a stress amplitude of 265 newtons per square millimeter. Under this stress amplitude, it broke after 43,600 load cycles. And these are the results of the other specimens which have been tested by us. When additional specimens are tested and the results are displayed as a curve, it becomes clear that this material will not break below a certain level of stress amplitude, even after a very large number of cycles. This stress level is termed fatigue limit sigma capital A. For most steels with body-centered cubic structure, the fatigue limit is reached after 10 million load cycles at the latest. It must be noted that the experimental results scatter considerably. Therefore, instead of a sharp curve, a statistically defined scatter band is commonly used. Of course, most users don't load their components with a constant cyclic load, but rather in an irregular manner. Therefore, these components have to be tested under this type of loading, termed operational loading. In this test rig, critical bicycle components are loaded similarly to practical use. Stem and handlebar must endure the typical bending and torsional loads for a sufficient number of cycles. Only then they are approved for serial production. Moreover, the fatigue strength does not only depend on the material. The mean stress has an important influence, the shape, the surface quality, environmental conditions, and much more. Not an easy story. Before an aircraft is allowed to take off for the first time, it has to go through extensive stress tests. The wings and many other elements are cyclically loaded in large test rigs. This later ensures the safe operation of the aircraft. Nevertheless, particularly important components are repeatedly examined for fatigue cracks in the course of operation. The tram, for instance, has to go into the test hall at regular intervals. Experienced staff use ultrasound to examine special components, especially the wheel set axles, to check whether they are still in perfect condition. Aircraft are also inspected for fatigue cracks at reasonable intervals. This helps us to depart for air travel without worry and land again safely.
Okay, so we have gone through the video for tests. We will discuss about the test more after a break. Okay, let's take a 10-minute break or 15-minute break. Please come back at 9:15. Okay, 9:15 we will start the lecture again. Okay. Did you guys hear me? 9:15 the lecture will start again.
Okay, doctor.
Okay, so we'll start now. We'll continue with the lecture. Are you guys there?
Yes, doctor.
Yes.
Okay, so let's continue now. Now we just saw an experiment for stress life method where they applied tensile and compressive loads in cycles and completely reversed loading, just as we have explained in the notepad here. And we defined amplitude of stress, and the mean value of stress in this particular case is 0. While we apply the load, for each experiment, for each specimen, we come up with a failure point. So failure point in a diagram which is called as a SN diagram. What is S? S here is the y-axis. The y-axis stands for the amplitude of stress, which we have calculated in this way. Okay. Remember, in cyclic loading, the stress is not constant. So on the y-axis, we have the amplitude of stress. For a particular amplitude of stress applied on the material and undergoing certain number of cycles, we have a failure point. So each of these points means one experiment conducted with one specimen until failure. So you can see here, this is a quite time consuming, expensive experiment to conduct and come up with the curve given here. In the video you saw for steel, the test was conducted for steel specimen with BCC structure. Now the material with BCC structure usually has different behavior in comparison to materials which have FCC structure, for example, aluminum. Okay, so this result is for steel with BCC structure. Most of the materials with BCC structure, they exhibit a phenomena which is called as the endurance limit. What is this endurance limit? When you reduce the amplitude of stress below a certain value called as the endurance limit, then the specimen will have infinite life. That is, the specimen will never fracture. But when it reaches endurance limit, the specimen fractures, begins to fracture. And this flattening out of the curve, which is known through experiments only. When I say experiments only, there is no theory behind this. We do not understand why this happens very clearly, but endurance limit for steel and other BCC structured material, they exist experimentally through experimental investigation. So for your steel specimen, SE value is around 50 PSIs. I think this is in KPSI, sorry. Kilopounds per square inch and not in SI units. So for steel, we get endurance limit. So for BCC materials, endurance limit exists. There is another name for this, and that is the fatigue limit. It is also called as fatigue limit. We can refer to it by both the names, this particular property. Now, just like yield strength, in the same way, for fatigue, we have to use the property which is called as endurance limit or fatigue limit, and it is represented by the symbol SE. For yield strength, we write it as SY. For endurance limit, we write it as SE. Okay. So this is the property for fatigue applications. Okay, let's further go through the graph, how the graph is plotted. We have on the normal scale the stress values given here, but on the x-axis, the number of cycles, they are written in logarithmic scale. So they are not exactly written on the normal scale here, and the values of number of cycles are directly given here at the each of this point. One cycle here, 10 cycles here, 100 cycles, 1000 cycles, and you can see it is not on the normal scale but logarithmic scale. Okay. Now usually the endurance limit or fatigue limit is reached for most of the materials around 10 power 7 cycles or 10 million cycles. When it reaches 10 million cycles, then the endurance limit or fatigue limit is reached for most of the BCC structured materials. However, if you go for FCC structured materials, then there is a problem. We do not have any endurance limit or fatigue limit experimentally. Okay, we cannot find any endurance limit with respect to that. Now again, all these are found through experiments. There is no theory behind it. We still do not understand why endurance limit exists for BCC materials and it does not exist for FCC materials. We have no idea about it. Okay, no proper theory behind that. Okay, so let's go for aluminum. For aluminum, how does it look like? The same SN diagram for aluminum looks like this, and you can clearly see even after it reached 10 million cycles, the curve is still going down. For sand cast aluminum, this is the range of values. For wrought aluminum, this is the range of values. For mold cast, this is the range of values of the SN diagram. Experimental results will have anything ranging, any point ranging between here. So what do we do with aluminum? Since experimentally no endurance limit exists. So what do? We pick 10 million cycles, and let's say we fix the point and we call this point as fatigue strength. We do not call it fatigue limit. We do not call it endurance limit, but we just, since it is not a limit, it is not flattening out, so we cannot call it limit. So rather we are going to call it as fatigue strength of aluminum. So we arbitrarily pick at 10 million cycles and then we call this value as the fatigue strength of aluminum, and then we will use that in design. Sometimes they pick it at 1 million cycles and sometimes maybe 100 million cycles. Depends upon what is the data they are providing as fatigue strength. Fatigue strength could be provided at 10 million, 1 million or 100 million cycles for aluminum. Okay. Mostly in design cases, you will have in 1 million cycles for aluminum. So let's go back to the figure. As I said earlier, the German guy who first did this experiment for railways back in the 19th century, that is 1857 or some other time, the guy was named Wöhler, and he's the first guy who came up with this experiment, and we follow his experiment even today. Okay, there is no improvement except in equipment design or testing machine design. Besides that, the experiment is exactly same what he did. Okay, so it is also called Wöhler curve. Now in the SN diagram you can see various regions from 1 to 1000 cycles. Up till this 1000 cycles, it is called as low cycle. So if we are within this range, we better do not follow the stress life method. Remember, the SN diagram here is for stress life method. So we will not use any equations from stress life method if we are within this region. If the failure region is between 1 to 1000 cycles, we need to use strain life method, more accurate methods. We can see here the stresses, amplitude of stress, they reach even the ultimate strength value. This is the ultimate tensile strength value here. Okay, so we are much above the yield strength of the material in this case. So we cannot use in that case stress life method, and in this region we will always use strain life method, which we will see later. Okay, now in the stress life method, the range within which we can work is the high cycle fatigue, and it starts from 1000 cycles or greater rather greater than 1000 cycles to higher number of cycles, maybe 100 million, 1 million, whatever it is. Okay, so if we are within this range, we can definitely use the equations which we are going to see further in a few slides, all these stress life equations. Okay, so this is the high cycle. Also, you can carefully see that below the endurance limit for the BCC structured material, be it steel or any other material, the life is infinite. So I don't need to predict what is the life of the specimen if I am below the endurance limit. It is infinite. However, if for steel in particular here, if my number of cycles for life is between 1000 and 1 million cycles, then I need to exactly predict what will be the number of cycles I can expect before failure happens. Okay, so in this region, we have to come up with a relationship, an empirical relationship by the curve fitting method here, between the amplitude of stress for completely reverse loading and the number of cycles to failure. So there is another equation which we will go through here as well. Suppose if we want to use the stress life method somehow in this region, there is also a empirical relationship between the amplitude of stress and number of cycles to failure in this region as well. So there are two sets of equations we will see for the life prediction later for these two regions. Below this, we have infinite life. We don't need to predict any life. We don't need any equation because it is infinite life. In the same way, for aluminum as well, we can come up with equations. However, in this chapter, we are going to see equations only for steel, because steel is extensively used used material in design applications. Suppose if you want to get some data for aluminum or some other material, how do you get it? Open ANSYS, and you will see material properties for different kinds of material, including steel, aluminum alloys, copper alloys, etc. Different alloys could be selected, and in fact you can extract the material properties even for fatigue in the case of other materials from finite element packages like ANSYS and other packages. Okay, all right, so now let's go to strain life method. In the strain life method, what do we do? What kind of experiment is done? In the stress life method, we controlled the stresses applied on the material. Okay, we control the maximum stress and minimum stress. Until fracture happens, we applied the same cycles. When I say one cycle, the cycle of load, it means starting at this point A, passing through B and reaching point C. From A to C consists of one cycle, and life calculations are based upon this cycle measurements again. Okay, since I did not define cycle, I am defining cycle. One cycle is this. So 1 million cycles means I apply the stress 1 million times like this before failure happened or until failure happens. So this is for stress life method. We control the stress applied on the specimen. In the strain life method, what do we do? We control the strain applied on the specimen. In experiment, in the stress life experiment, we took a specimen. I'm going to approximately draw the specimen here, not the exact shape, but this is what we did in the stress life method. We applied P, tensile and compressive load, on the specimen until failure, controlling the load applied through the springs. Okay, now what we are going to do is Imagine on the machine you remove the spring and you control exactly what is the strain you apply on the specimen. So instead of the load P, I am going to apply exactly the delta L values to the specimen. The elongation of the specimen will be controlled. By controlling the elongation, I can control strain applied on the material. If I do the same experiment with strain as the control, then the test becomes a strain life method result. Okay. Also, we saw that the strain life method was conducted or should be conducted in the region of low cycles. So it is likely when I apply the strain that plastic deformation also can take place, because we could be reaching yield strength or higher than the yield strength of the material, and therefore plastic deformation takes place while I conduct the experiment for strain life method. So here strain, instead of stress, I control the strain in completely reverse fashion in the same way as before. And the magnitudes of maximum strain is equal to the minimum strain. And we do the same kind of completely reverse loadings tests, and we plot strain versus number of cycles to failure instead. Okay, so again we have the amplitude of strain defined in the same way. So it should be minus min over 2. So this should be equal to exactly the maximum strain value. This will be your amplitude, and your mean strain in this case is exactly equal to 0 for our case. Okay, so this is equal to 0. Now what do we plot? In this case, since we have plastic strain and elastic strain, we plot number of cycles to failure in logarithmic plot, and we will have 2 to 3 different plots. Okay, so let's see here. Again, we will have similar kind of plots, one for elastic, one for plastic, and another for total strain. So let's go ahead and see the strain plot. I will come back to these two figures later. Let's first see the strain plot here. Amplitude of strain, rather delta epsilon over 2 he has written, so it's the same amplitude of strain. This is the elastic strain curve, the plastic strain curve, and the total strain curve. Okay, and number of cycles to failure. Here you can see again going from 1 to 10 power 6 cycles. Okay, so why did we split this into elastic and plastic strain and the total strain? Okay, there is a reason for that. When you apply the strain, when you take the material and apply the strain, let's draw the stress strain graph here. First, I increase the load, I reach the yield limit in some of the cases, cross the yield point and go to a point and reverse the load. What will happen? It reverses and follows a certain path. Okay, and then again I reverse the load here, again it follows a certain path. When it returns, it does not follow the same path. There is some strain hardening phenomena because we have reached the yield point. Once we cross the yield point, we know that after one cycle, again the yield point will keep on changing. Every time I do cold work on the specimen, the yield point will change, and because of that, the curve is going to change at each point. So this is a strain softening material. Why do you call it as a softening material? Because the yield point keeps going down. You can see here at a later stage yield point is here. In the first stage yield point is here. In the second stage the yield point has come, let's see here, here in this curve, and in the third curve yield point is here. So yield point is decreasing, so it is a softening material, and the curve keeps on changing like this. But after I repeat the application of the load several times, at one point it will stop changing and the curve stabilizes. The stress strain curve stabilizes like this, and it will keep on repeating on the same curve after a certain number of cycles. Now, if you take any number of cycles from here to here, elastic, or if you take the entire cycle starting from here, we can consider from here to certain point here, and then I release the strain, then there is elastic recovery here, and then there is the permanent plastic strain here. So the total strain relative to this point starting from here to here, we can think of this entire strain as consisting of permanent plastic strain and elastic strain. So there is a split of strain into elastic component and plastic component. Okay, and therefore in the strain amplitude versus number of cycles to failure, we can also split it into elastic strain and plastic strain, and when you add them together you get the total strain curve. Okay, so in this curve there are a couple of constants we need to go through. Okay, so there is the point of intersection between the total plastic strain curve and the y-axis here, and this point of intersection we are going to call it as fatigue ductility coefficient, epsilon f prime, and this can be obtained graphically. Okay, in the same way, between the elastic curve and the y-axis there is a point of intersection, and that point of intersection is given by epsilon f prime. We can for the elastic strain, epsilon f prime can also be written, because we are within the elastic limit, we can use the Hooke's law, E times epsilon, and reverse it, and we can write it as sigma f prime over E. So that is what is written here. Here sigma f prime is called as the fatigue strength coefficient. Okay, now why do we need these intercepts? Because we need an equation to represent the relationship between strain and number of cycles to failure. Okay, again in the previous case for stress life method we did not come up with the equations. We will come up with these equations later, but in the strain life method we are going to see the equations here only. To get the equations we need these 2 points and the slopes here, the slope B and the slope C. Slope B for elastic curve, slope C for the plastic strain curve. Okay. Okay, so if we have these quantities together, we can add them up together and we will get the relationship between the total strain and number of cycles to failure, and that equation can be used to figure out what is the life of the specimen. That is the idea. Now to the slopes, the slope C for the plastic curve, it is called as fatigue ductility exponent C, and the slope B for the elastic curve, it is called as fatigue strength exponent D. Okay, with respect to the elastic curve, it is called fatigue strength coefficient and fatigue strength exponent. With respect to plastic curve, it is called fatigue ductility coefficient and fatigue ductility exponent. Elastic strength, and for plastic we call it ductility. Okay, so that is the only difference here. Coefficients and exponents. Okay, why do we call it exponent? Because there is a relationship between strain and log of number of cycles to failure, and this log is the natural logarithm, could be log 10 base, and therefore the slope comes out as an exponent, and therefore we call it as exponents. So let's write the equation for strain. Total strain is elastic strain plus plastic strain. For the curve, an empirical relationship can be obtained for the plastic strain curve through the fatigue ductility coefficient and fatigue ductility exponent C. These two values are usually obtained from the graph here for different materials. N is the number of cycles to failure. So we have a relationship here. Now similarly for the elastic curve, we have the fatigue strength coefficient and fatigue strength exponent, and we can relate the strain to the number of cycles to failure. So we have plastics, elastic, add them up, we get a single equation, and this equation is called as Manson-Coffin relationship. From this relationship, we can obtain the life of the specimen. Okay, what would be the life of the specimen? For example, if I know what is the strain applied on the specimen or component at a local point, maybe the highest strain, from the strain value, knowing all these constants, fatigue strength coefficient, fatigue strength exponent, fatigue ductility coefficient, fatigue ductility exponent, knowing these values, I will be able to calculate what is the number of cycles to failure. Okay, we can solve this equation and get the number of cycles to failure. How do I get these constants? Table A23 in your book gives these values. So let's go to table A23 in your book. Okay, so I think we went a little bit down. 21, we have 22 and 23 over here. Let's turn it here. We can see this is the fracture at strain. Sorry, here we have the fatigue strength coefficient, fatigue strength exponent, fatigue ductility coefficient, and fatigue ductility exponent for different types of materials according to the standards. We can see several materials are listed here, and you can get these constants from the table over here. Okay, so using these values, you will be able to figure out what is the life of the specimen. Or if you want to have a specific life for the specimen, you can substitute here and you can check what is the maximum strain you can apply on the specimen, so that you can design the component by controlling the strain and other parameters in the design. Okay, so the same table is given there. Okay, now usually when we design materials using strain life method, this strain, maximum strain in the component cannot be found that easily. You cannot do hand calculations and figure it out, because your component can be quite complicated in design. If that is the case, we have to run the finite element analysis, and we have to find where the local strain is maximum. And we have to figure out what is the plastic strain, elastic strain, and then from that result, we will be able to figure out, using Manson-Coffin relationship, what would be the life of the specimen. So we need a combination of experimental results and finite element analysis to actually do strain life calculations, much more accurate strain life calculations. However, in the stress life method, we don't necessarily need the finite element calculations because we are in low nominal stress region. Here we are in high nominal stress region. Is it clear? Is it clear?
Yes, doctor.
Okay. Okay, so then I think we have less time now, about 5 minutes. I'm going to stop right here. And next class, we will discuss about linear elastic fracture mechanics. And we will see if a crack is present, how to use the stress intensity factor and critical stress intensity factor or the fracture toughness values to obtain the life of the specimen. Okay, so if you don't have any questions, I'm going to stop right here and we will meet again on Sunday. Any questions? By the way, before we leave, I want to get a timing for the midterm test or the test 1. For test 1, I have fixed the date as 7th of April because there is no other date which I can do the test. 6th of April, I have another test to be conducted. So 7th of April, what would be the time good for you guys for the test? So 7th of April is on a Thursday.
I don't know, doctor. We will ask.
Afternoon.
Doctor.
It's good, doctor.
What? I cannot hear. Guys,
I
I
said
cannot.
afternoon, doctor.
Afternoon. So afternoon about 1 o'clock. Is that fine? 1
No,
p.m.
doctor. We have lectures. It will be better if it's 4 p.m., 5 p.m.
From what time you have lecture? Can you please let me know now? What time you have lecture?
Well, I have lecture from 1 p.m. to 2 p.m.
1 p.m. to 2 p.m. So in that case, we have to put the test on 11 to 1 o'clock. Is that fine?
I also have doctor. I have lecture all the day.
No, the lecture, it is my lecture, right? At oh, okay. So you guys are at 8. 11 o'clock, what lecture you have?
You can't make it 4 p.m. doctor.
4 p.m. it will
Or
be
3 p.m., doctor.
3
Yeah, 3 p.m. is okay too.
3 p.m. is fine. Okay, because it will be late. You'll be fasting, right? That's why I thought I will finish earlier. Yes, morning time. Okay.
It's okay,
Because others
doctor.
might. I'm thinking since you guys are fasting, I don't want to be too late. Reaching your time. So if 3 is okay,
Doctor, we
yeah.
will discuss with the group first and see.
Okay.
I will tell you.
Okay. So what I will do is on 7th of April, I will create a poll and you guys discuss and let me know. Okay.
Okay, doctor.
Okay. Okay. Okay then. See you guys. So I will meet you again on Sunday. Okay. See you.